And we are finally here at the end of the proof of Brooks' theorem. Brooks' theorem, proof part 3. In some sense, the sequence in which I've presented these results is a little bit perhaps unpedagogical, in the sense that this part 3, kind of the final case, is actually the very natural, kind of general, generic case of how the proof works. So let's see what it is in a nutshell. So Brooks' theorem says, suppose you have a simple connected graph, not complete and not an odd cycle. We want to know that the chromatic number is less than the maximum degree of a vertex, less than or equal to. Okay, well, so the argument is as follows. You suppose, so there's the general argument. Suppose that you can find 3 vertices, u, v, and w, such that, well, you remove 2 of them and you're connected, and such that u and v are connected to each other, v and w are connected to each other, but u and v are not connected to each other. So, the picture is something like this. We have u, v, and w. U is connected to v, v is connected to w, but these two guys aren't connected. Then if we have this situation, here's how the argument goes. So I'm just going to prove Brooks' theorem in this case. So what do? We list all the vertices that you get when you remove u and w in an ordered way, v1, v2, v3, all the way up to vl, which is the vertex v. But we do it in such a way that we do it in decreasing order of distance to v. So the last one is the closest to v, and the earlier ones are farther and farther away from v, going to v1, which is as far as possible to v. So one should just preface this by saying, to have a notion of distance, which is the length of a minimal path connecting two vertices, the graph had better be connected. And so we're using this assumption that when you remove these things, you're still connected, and just the way we're phrasing this already. Okay. So, so notice, VL minus 1, the one right before VL, is a distance of 1, because that's the closest you could get to V, and therefore it's adjacent to V. The guys on the next step are distance 2, etc. Okay. So in particular, what do we know? We know that as the indices go up, if you go from I to J, the vertices get closer and closer to V. That's what we're saying. Okay, so we're imagining some picture like this. I guess this should be an L minus 1, and this V is VL. And we're imagining, we start at V, which is VL minus, that was supposed to be a 1. I'm not sure what I just wrote there. L minus 1. And then we merrily march our way further and further, ending at V1. All right. Now, so now look at one of these guys, some VI, somewhere out here in the middle of things. Let's suppose that it's, at least a distance 1 away from the vertex V, which is really just to say that it's not V itself, right? Because distance 0 would be V itself, and that's as close as you can get. Well, then, what do you know? It's going to have to be adjacent to something which is closer to V, and therefore something with a larger index. Because if you think about it, right, your VI has some distance away, so there's some minimal path of that particular length k connecting VI to V. And as you go along that minimal path, everything along it is, when you follow that path is also, the remainder of that path is also a minimal path. So the first step along, you'll get something that's distance k minus 1 away, et cetera. So, and then that has to have a higher index. Okay. So what does that tell you? It tells you that you have to be adjacent to something which has a bigger index. Okay. Everything in that list is adjacent to something with a bigger index. So now we can state the algorithm. The algorithm is, okay, step 1, you color U and V, your original 2 vertex, color number 1. Okay, now, as you go along, you color these other guys in order, starting from the furthest and going to the closest. And we use each time the first available color from the list 1 up through capital delta. The only question is, why does this work? Well, we just need to show that at each step, you can still keep doing this process. So if we look, somewhere along the path, like let's say we're not all the way at the end, if we're not all the way at the end, then there's something further down on the list that you're going to be adjacent to, because there's, if you're not all the way at the end, then you have a smaller, the vertexes can still increase, and there'll be something with a bigger index that's adjacent to you. Okay, but what that means is that when we're coloring this vertex vi, there's something that's adjacent to vi with a bigger index, and that thing with a bigger index has not yet been colored since we're coloring them in order. Well, because it's not colored and it was adjacent to you, that means that the vertices that have been colored are at most delta -1 in number. And therefore, there's there's at least one color from 1 through delta that hasn't been used, and we can continue the process and use that to color VI. The only thing that we now need to figure out is what happens at the very end when you get all the way to V. Well, when you get all the way to V, realize where you are. You have these two guys that are adjacent to V in that original diagram. We have V and we have U and we have W, and these two guys are adjacent to V, and we gave them in the beginning color number 1. Okay. Now, because they have color number 1 and V has at most delta neighbors, then, well, that says that the neighbors have at most delta -1 colors, because 2 of the neighbors have the same color. So you can't have the full delta colors. 2 of them have to be the same, which means there is one color you haven't used, and poof, we're done. But are we done? What's wrong with this proof? Well, just the starting point. Why is it that we were able to assume that we could find these U, V, and W as stated, such that this is, you remove 2 of them, you're connected, and such that these guys are connected and these ones aren't? Why could we have assumed that? Well, part of it isn't too bad. It goes into the following lemma. If you have a connected graph which is not complete, then you can always find 3 vertices with this property, with the first 2 connected, the second 2 connected, but the first and the last one not connected. So let's just see this real quick. Well, the proof is going to go by contradiction. So we suppose that this is not the case. That is, suppose you have a complete graph such that whenever you have 3 vertices such that the first is connected to the second is connected to the third, then this is also connected to the last one. So suppose you have this situation. Well, if you're not complete, then you can find 2 vertices that are not connected to each other. We're going to argue by contradiction, right? So now, because G is a connected graph, you can find a walk that goes from X to Y, V1, V2, V3, up to Vm, where the first one is X and the last one is Y. Well, now, by assumption, well, we know that V1 is connected to V2. These are just along some walk, so they're all successively adjacent to each other. V1 is adjacent to V2, V2 to V3. And if we're arguing by contradiction, we have to assume that this thing doesn't hold for any triple. So therefore, we have to have V1 is adjacent to V3. Now, again, V1 is adjacent to V3, but along the path, V3 is adjacent to V4. So again, because this is not true for any triple, we have to have V1 adjacent to V4. And you continue this on, and eventually you get V1 adjacent to V5, V1 adjacent to V6, and eventually V1 is adjacent to Vm. But guess what? V1 was X and Vm was Y, and we assumed in the beginning that they were not adjacent to each other. And therefore we get a contradiction, and that contradiction is the proof of our lemma. All right, so let's go ahead and take a look at Brooks' theorem now, the proof of Brooks' theorem. So suppose you have a graph which is not complete, not an odd cycle, and connected. Well, let's assume by contradiction that the chromatic number is bigger than capital delta. So Brooks' theorem says that it has to be less than or equal to. So what if it was bigger? Well, we could remove edges and make our graph critical without changing the chromatic number. So when we do that, remove edges, the chromatic number stays the same, because that's the point. But we might have fewer edges, which makes delta at most go down. So doing that, we preserve that inequality. Chi of G prime is still bigger than capital delta, because capital delta only got smaller. Additionally, if G wasn't complete, you're not going to make the new one complete by removing some edges. And we can also assume that we weren't, that you don't get an odd cycle still in G prime, because what if you did? if you did have an odd cycle, well, what's the chromatic number for an odd cycle? It's 3. So this would be 3. Capital delta of an odd cycle is 2, right? But remember, so every single vertex has degree 2. If we know that G wasn't an odd cycle, so if we remove edges and make it an odd cycle, then we would have had vertices whose degree was strictly bigger than 2, which means we would have been in the context of chi being 3 and capital delta being at least 3. But that means that that chi wouldn't have been strictly bigger than delta in that case. So that couldn't have happened. So you don't have an odd cycle still. So without loss of generality, we can assume that we actually have a critical graph, because if we have a counterexample, then we can find a counterexample that was critical. That's the point. Okay. Now we've seen in the previous video that if you're critical, then you're a block. So we can assume we have a block, no cut vertices. What if you have a 2-vertex cut? Well, if you have a 2-vertex cut, we saw in the last video that Brooks' theorem has to hold. So we're assuming it doesn't hold, so we don't have a 2-vertex cut. So in other words, our graph is at least 3 connected. You have to remove at least 3 vertices to disconnect it. Well, now, because G is not complete, by that lemma, we can find UV and W, such that UV is an edge, VW is an edge, but UW is not an edge. Okay? But now you're 3 connected. So whenever you remove any 2 vertices, you're connected. Well, that means we have the hypotheses of our previous argument. So Brooks holds in this case too. So to summarize, we know that if G is a counterexample to Brooks' theorem, then we can find another counterexample, the smaller G prime, and we can show there that G prime isn't a counterexample. But that tells us there can't be any counterexamples, which tells us Brooks' theorem is true. And that is the end. Thank you.